non-dimensionalization of the basic equation. The basic equation. We could use the Part8 method of the previous section to analyze problem after problem after problem, finding the dimensionless parameters that govern in each case. Textbooks on dimensional analysis do this. An alternative and very powerful technique is the attack to the basic equation of flow from the Navier-Stokes or conservation equations in Chapter 4. Even though these equations cannot be solved in general, they will reveal basic dimensionless parameters, such as the Reynolds number, in their proper form and from position, giving clues to when they are negligible. The boundary condition must also be non-dimensionalized. The conservation equations such as continuity, momentum equation, and in the constant viscosity, we have the relation for conservation of mass, which is continuity in the incompressible flow and constant viscosity. We have the relation equals to 0 for continuity, and for Navier-Stokes or momentum equation is in 3 dimensions. We have rho dv on dt equals to rho g minus typical boundary conditions for these two equations are, so these two equations have a specific boundary condition, which is v equals to 0, fixed surface, inlet or outlet, P and P. And free surfaces on fluid, we have a for z equals to eta d eta on dt, and p equals to pa minus gamma rx r1. This is the boundary condition. We omit the energy equation and assign its dimensionless for in the problems. These two equations contain three basic dimensions are, so we can write the basic dimensions for these three equations are the dimension in the continuity equation and Navier-Stokes equation are M, L, and T. We have three dimensions. And all variables are dimension. Variables are P, V, X, can be non-dimensionalized by using density and two reference constants that may be characteristic of the particular fluid, reference velocity and reference U and reference length. L. What is reference velocity and reference length? For example, U may be inlet or upstream velocity and L the diameter of a body immersed in the stream. Alright, for example, inlet or upstream velocity and length, for example, can be a diameter of a body, for example, a diameter of a body immersed in a fluid. So we can non-dimensionalize the, for example, velocity at the, with considering the reference velocity, which give us the relation for dimensional velocity, and this is U. Equals to L X star equals to set on L, for example, for diameter if we have, and T should be non-dimensional with U and L, and at the end we must obtain a P equals to these are the non-dimensional form of geometry and time without pressure. All these are freely abused except the pressure, non-dimensional pressure, where have introduced the piezometric pressure, assuming that Z is up, this is high, This idea suggested by Bernoulli's equation. Since rho, u, and L are all constant, the derivative in the equation of Navier-Stokes continuity cannot be handled in dimensionless form with dimensional coefficient. For example, if we want to calculate rho u and rho x in the continuity equation, we can write non-dimensional multiplied to the reference velocity, where u star equals to round so we can obtain the non-dimensional form of the derivation of velocity in x direction. Substitute the variables obtaining from the non-dimensional form of variables in the Navier-Stokes and continuity equation and divide through the leading dimensional coefficient. In the same way, we can obtain the continuity equation in non-dimensional form. And for Navier-Stokes or momentum equation, we have this relation, non-dimensional form of momentum equation, star minus plus the dimensionless boundary condition are fixed wall, inlet or outlet, below, and P also star. We obtained previous relation, free surface. On dt star and P star equals to PA on rho U2 plus GL on U2, which are our reference quantities. These equations reveal a total of 4 dimensionless parameters, 1 in the Navier-Stokes equation and 3 in the free surface pressure boundary condition. Dimensionless parameters in the Navier-Stokes conservation equations. Dimensionless parameters. In the continuity equation, there are no parameters. The Navier-Stokes equation contains one generally accepted as the most important parameter in fluid mechanics, Reynolds number, which is rho u L on mu. It depends on the our reference and the fluid property. It is named after Reynolds in the 19th and 20th century, a British engineer who first proposed this relation. The Reynolds number is always important with or without a free surface and can be neglected only in the flow regions away from high velocity gradients, for example away from solid surface, jets or waves. No slip and jet inlet exit boundary condition contain no parameters. The free surface pressure condition contains three Euler number, EU, this is named after Leonhard Euler and is rarely important unless the pressure drops low enough to cause vapor formation in a liquid. And the pressure low enough to cause formation of vapor. In a liquid. The Euler number is written as a pressure difference also in this expression, EU equals to pressure difference on rho U2, U squared. If delta P involves vapor pressure, PV for example, is called the cavitation number. If delta P involves vapor pressure, it is called the cavitation number. Which expressed as this relation. For cavitation number we have the relation for PA minus P vapor on rho u square. This is the cavitation number. The second free surface parameter is much more important, rho number. Fr It is named after William Fruit, a British naval architect who, with his son Robert, developed the ship model towing tank concept and proposed similarity rules for free surface flow. The flow number is the dominant effect in free surface flow and is totally unimportant if there is no free surface. So if there is no free, not important. If there is no free surface. In the next chapters, investigate flow number effect in detail. The final free surface parameter is Weber number. Rho u2L on gamma. It's named after Moritz Weber of a Polytechnic Institute of Berlin who developed the laws of similitude in their modern form. It was Weber who named Reynolds and Freud after Reynolds and Freud. The Weber number is important if it is only if it is of a order unity or less, which typically occurs when the surface curvature is comparable in size to the liquid depth, such as droplets, capillary flows, ripple waves, and very small hydraulic bodies. Droplets, capillary flow, ripple waves, and very small hydraulic bodies. If there is no free surface, Freud number and Euler number and Weber number drop out entirely except for the possibility of cavitation of liquid at a very small Euler number. Thus, in low-speed viscous flow with no free surface, Reynolds number is the only important dimensionless parameters. So we can take a note here. In low speed viscous flow with no free surface, viscous flow with no free surface, The Reynolds number is the only important dimensionless number. Reynolds number is the only important dimensionless The next dimensionless number related to compressibility parameters. In high-speed flow of gas, there are significant changes in pressure, density, and temperature that must be related by an equation of state such as the perfect gas law. The thermodynamics change introduced two additional dimensionless parameters mentioned briefly in earlier chapters as Mach number specific heat ratio, the Mach number is named after Ernst Mach, an Austrian physicist. The effect of K is only slight to moderate, but Mach number exerts a strong effect on compressible flow properties if it greater than 3/10. These effects are studied in next chapters. 3/10 is the criterion for the compressible and incompressible assumption, usually in the simplified problems. The next dimensionless number is related to oscillating flow. If the flow pattern in oscillating a seventh parameter enters through the inlet boundary condition, for example, suppose that the inlet stream is of the form U So, as previously said, for U star equals to U on the reference U and T star T U on L. Non-dimensionalization of this relation results in U on U equals the argument of cosine contains the new parameters St equals to Struhan number omega L on U. The dimensionless force and moments, friction and heat transfer and so on of such an oscillating flow would be function of both Reynolds and Struhan number. This parameter is named after Struhan, a German physicist who experimented in 19th century with wire signing in the wine.